So our next speaker today is Professor Jesse Capecelatro from University of Michigan Mechanical Engineering Department. So Jesse is a good friend. We had overlap of 2 years at Cornell, and he's one of those rare theoretician or simulation person who is not only good in his work, he also good with building things from his hand, doing other stuff like wrestling, tango, all the cool stuff we can look for. So Jesse, I'm looking forward to your talk. As always, I'm sure you will do a great job.
Great, thanks. And it's a real treat to give this talk. So, obviously Bala is just such a big player in this field, but I'd like to say, one thing I really admire about Bala, beyond obviously the great science he does, is how much he promotes multi-phase flow as a discipline. The IJMF spotlight is a great example. He always puts the field itself, I think, first, and often is really championing young researchers as well, which is really important for this field if we want to see it flourish and do well, is to be welcoming to some of the younger students and younger researchers in this area. And Bala is just does a great job at that. So I really appreciate that. And it's great to see you, Himanshu. It's been a while. So let me share my screen and find my slides. Here we go. So this talk's maybe a little different in the sense I'll be showing some of my work at the very end. I see this as a review. I wrote a review article, well, not really a review article. I've been funded by NASA since I joined Michigan and really jumping into this field of compressible gas particle flows, which is, I hope to illustrate here, is just very rich in multi-phase physics. Compared to incompressible flows, which incompressible multi-phase flow has, a lot of challenges. And as we just saw from Shankar's work, still a lot to be done. But amplify that by at least an order of magnitude when you start looking at compressible flows. And so it's an exciting area. And when I started working on this around 2016, it became apparent that just how much there is to do, how much is unknown, and how much Bala has contributed to this area. And so I wrote an article, it's on archive right now, and I'm basically summarizing a lot of that here. And then towards the end, showing some recent work that we've done to look at some modeling. So we're focusing on compressible or high-speed gas particle flows. The application that motivates my work and the reason NASA cares about this has to do with spacecraft landing. And so I thought I would start off by showing this video of, this is from the February 18th Mars 2020 landing. So this is the Perseverance rover. And what we're seeing is the deployment of the rover, which is absolutely amazing. It was very exciting when this footage was coming out. So this was, a couple months ago, and this on the right, we're seeing the erosion. So the exhaust plume is eroding the surface. And the reason they're using this so-called sky crane maneuver, where they're hovering at 30 feet above the surface of Mars and lowering the rover, is to prevent the exhaust plume, the rocket engines, from getting too close to the surface, because there's a lot of issues that happen as the exhaust plume gets very close, most of it driven by the multi-phase physics. And even though this is 30 feet above the surface, you can see the stagnation zone, significant high-speed erosion, and you still get large rocks dislodged. And in fact, the landing, the sky crane maneuver 10 years ago with Curiosity, during the landing, a rock got dislodged and damaged the wind sensor. So there's still issues using the sky crane maneuver. And then beyond that, future missions sending people to Mars or sample return missions, you won't be able to use sky crane. So we have to figure out ways to get the rocket exhaust close to the surface. Just really quickly, because I think this is probably a newer area or application to most of the people here. These plume surface interactions, there are a number of examples from previous landings where this has been significantly led to almost mission failure and other challenges. So 4 of the 6 Apollo landings have suffered from hindered visibility. So this is sort of a camera view of the InSight landing a couple of years ago, and completely lost visibility due to the amount of dust and particles that got dislodged. Lunar dust was found in deposit on equipment 17 meters from Apollo 11 and 160 meters from Apollo 12. So on the moon, the lunar dust just travels really far. And some of this has led to damaging hardware, or essentially what the NASA researchers have called sandblasting of hardware by nearby equipment. The Apollo 15 lunar module almost fell over upon touchdown because of this. And in fact, some of these particles are thought to have traveled near very close to escape velocity. And so, you're landing on the moon, dislodging dust that gets into orbit of the moon and affects satellites. So it's a real challenge. And this is showing some craters that were formed under the Curiosity's rover from the exhaust plume. And if we kind of look at what's some of the relevant physics, so we have a high-speed jet or out of the nozzle of the rocket. There's a compressibility effect. So we have Mach disks, expansion fans. At the surface, if this is a multi-phase flow problem, we characterize this by volume fraction. So we get everything from closed packing in the surface. And then as you move up, the volume fraction gets very low, but travels very fast in these shear layers. You get a plate shock that forms above the surface. And a recirculation zone inside this crater. You get erosion, and you get both subsonic, supersonic flow. So we have to deal with volume fractions from dilute to dense. We have to deal with subsonic to supersonic gas phase. And outside the plume, the flow is rarefied. But for now, everything I'll consider is physics relevant inside the plume, where we can assume that the flow is continuum. Very hard problem, but it's also a very exciting problem. For incompressible gas particle flows, we have a large range of space and time scales to reconcile. So, if we think about just a simple case of a single particle in a flow, we have the boundary layer thickness, the Kolmogorov length scale or time scales if there's turbulence, the particle diameter, the length of the wake, the particle response time. But now if the flow is compressible, we have shock wave thickness, which can be on the order of angstroms, so much smaller than particle diameter, and then acoustic timescales. And so what I'm showing here is just an example. If we had a 100 micron particle with a density of 3,000 in air traveling near Mach 1, irrespective of its speed, the particle response time is about 1/10 of a second. But now the acoustic time scale based on the diameter and sound speed is 0.3 microseconds. So now we're introducing new time scales, orders of magnitude smaller. So it's a hard problem. And this is just showing an example of one of the simulation that NASA Marshall has been looking at with their lunar Apollo lunar landing. And so what we're seeing here is the grid resolution, and they have very fine resolution near the surface to try to resolve some of the multi-phase aspects. And if we were to zoom in, if we did a direct numerical simulation, so say many grid points across the diameter of each particle, we would need grid resolution on the order of 1 micron, but then the landing site spans 50 meters. So it's a truly, multi-scale, wide range of scales. Now, compressible gas particle flows obviously are not just relevant to landing, but also many other examples. So volcanic eruptions, coal dust explosions, and a lot of the applications that motivate the work Bala has been doing is related to detonation of heterogeneous explosions. And so, these flows and these regimes are relevant to lots of interesting but also important applications. So briefly, if we just look at the governing equations, so if we consider the gas phase mass and momentum, and we apply a typical volume filtering to allow us to solve for the equations at some scale larger than the particle, we're going to lead to unclosed terms. And so this should be familiar to many people that are that have done modeling of two-phase flows for incompressible flows, where we have a source term due to momentum exchange, such as drag and lift, and then a so-called Reynolds stress-like term that we sometimes refer to as pseudo-turbulent Reynolds stress because it's produced by particles. But the energy equation, we have even more unclosed terms. And so just briefly, this is the gas phase total energy. We now have a heat exchange term, usually modeled with a Nusselt number correlation. All of these terms in red are unclosed. And then the thermodynamic relation between pressure and energy also plays a role. And so the pseudo TKE has a direct effect on the pressure field. And some work we've done, and Bala has published also similar work showing that luckily many of these terms are negligible. And in the end, what's important if we wanted to solve, say, an average set of equations is the momentum and heat exchange, so interphase exchange, and then the pseudo-turbulent Reynolds stress is also playing a role. So, you know, we need models for these valid across Reynolds number, volume fraction, and Mach number. I would argue that in the last about 11 years or 12 years, there's been a lot of advancements. I mean, really exponential progress on this modeling, largely driven by Balachandar and his students, which has been very exciting. So if we consider just the forces acting on a particle, you know, the classic sort of BBO or Maxey-Riley equations we're all familiar with, we have drag, unsteady and viscous terms. So Bala and co-workers, so student Palmer, extended this to compressible flows in the limit of low Mach number and Reynolds number, but you know, it's a starting place for now adding Reynolds number corrections, Mach number corrections, and so forth. And you know, if we're considering these high density ratio flows, usually those unsteady terms are negligible for gas solid flows, so added mass and that, say, history. But when the gas phase is accelerating, so for example, a shock wave going past particles, now all of a sudden we do have to account for these unsteady terms. And so it's really challenging. I thought it'd be kind of fun to just focus, you know, there's a lot of unclosed terms. Let's just focus on drag and specifically drag in the continuum regime. So we'll assume the Newton number is low enough. And so we can determine that based on the ratio of Mach number to Reynolds number. So if we have very high Mach number and low Reynolds number, then we're moving away from the continuum limit. So we'll consider when we have high Mach number, we also have high Reynolds number. But just a brief history, what's been done for flow past an isolated sphere. So starting in 1687, I'd argue that you know, Newton, specifically in his second book of Principia, is where he introduced this notion of a drag coefficient. So showing that the drag force on a sphere is proportional to the area and velocity squared, and argued the drag coefficient is close to 0.5. Sometime later, George Stokes derived analytically Stokes drag law and showed that the drag coefficient is 24 of a Reynolds number. Now, about just a couple years later, Francis Bashforth, who is a British general who's doing a lot of work with ballistics, specifically related to musket fire, invented a means of measuring velocity from cannon fire that allowed them to get accurate representation or 10 velocity measurements per shot. And the nice thing was, shortly after this, they moved away from round shots. So here we have round spheres moving or cannon fire. And the unique thing about cannon fire is that the typical speed and size, we're dealing with Mach number between 0.3 and 3. So very relevant range and interesting range, and near the critical Reynolds number. So it's a perfect range for studying drag. And this was back in the 1860s. 1979, Miller and Bailey's JFM paper, they try to compile all of the available data on drag past a sphere at the time. And interestingly, that work by Bashforth was among some of the most accurate and reliable data they had at the time, and scattered no less than the other available data. And so 1970s, we were starting to get this map of drag past the sphere at different Reynolds numbers and Mach numbers. And the name Bashforth might look familiar because about 30 years after this, Bashforth and his colleague from, he went to college with, Adams, invented the Adams-Bashforth method, which many of us still use today as for numerical time integration. So it's the same Bashforth. Real briefly, drag as a function of Mach number is fairly constant until you get to Mach close to 1, but there's a lot of uncertainty and scatter, which is well acknowledged. Largely, you could argue because we're using a lot of this data is based on cannon fire. In terms of current models that exist, these are all models for single, we're not dealing with multi-particle yet, just isolated particle. One of the most popular models was from Henderson in 1976, who developed the Reynolds number, Mach number dependent drag based on a sort of piecewise functions from subsonic to supersonic. In 2008, Eric Loth developed a correlation where he sort of separated this into a rarefied dominated, compression dominated, and then proposed this sort of nexus that separates the two. But Palmer showed that, and Balachandar showed that the error in this sort of transitional regime near Mach 1 can be as large as 55%. There's a lot of uncertainty there. And so in 2010, Palmer proposed a new model based on this sort of critical Mach number. So if you're below this critical Mach number, you have this correlation. And then, so this is really fit based on experimental data. And the reason why you can do this is because the flow physics is very different. When you're sort of subsonic, you can get compressibility effects, but once you get to supersonic, you get this bow shock that plays a very large role in expansion waves that have an effect on drag. In 2020, Nagata performed some DNS and sort of started closing the gap at these transitional regimes. And just this year, a couple of months ago, Eric Loth with Nagata refined their model. And I believe it's the first model using numerical simulations as opposed to just experimental data to inform the correlation. And so there's a new drag law. The challenge is that's all for single particle. And so obviously, for incompressible flow, the past couple of years, there's been an explosion of data from pure DNS to inform volume fraction dependent drag. But the challenge is we now are at this point where we either have single particle drag laws at finite Mach number or incompressible drag laws at finite volume fraction. And so it's this sort of what's happening here when you have finite volume fraction and Mach number that's largely unknown and poses a lot of challenges. I know that time's running short. I'll just mention that probably one of the only models that exists currently was also from Bala's group, where they took the drag from Palmer and then combined it with Sangani's volume fraction correction. This volume fraction correction was for up to volume fraction of 0.3 and incompressible. But there's still a lot of uncertainty. Bala this year published some results kind of looking at shock particle interactions and trying to assess how well does such a model work. Others have done the same. And under certain circumstances, it works well, and under others, it doesn't. And so what my group's been doing in the last couple of years is trying to look at using highly resolved simulations to improve the drag models. One thing I'd like to argue is it's unlikely you'll be able, in most applications, you'll be able to sustain finite Mach numbers at high volume fraction. If you just think of the power that would be required to flow gas through a dense suspension at Mach 1, it's very high. And so this is an Euler-Lagrange simulation we did of a Plume and of Plume surface interaction. And what we see is a Mach number volume fraction PDF. And you tend to get very high probability of low Mach number at high volume fraction. So that's inside this dense bed. And then high probability of high Mach number and low volume fraction. So that's sort of in this ejecta region. And so I'm arguing that drag laws, at least for this application, should focus on sort of this intermediate regime. And I'll just briefly say we've been doing, spending a lot of time developing the numerical methods to do homogeneous suspensions of flows past spheres. across Mach number. So this is all Reynolds number 300, low Mach to Mach 1, and we all of a sudden start seeing bow shocks and shocklets form. What's interesting is that if we were to look at the turbulent Mach number as a function of volume fraction here, as you increase the volume fraction, the turbulent Mach number increases, even though the bulk Mach number is constant. And so you can imagine the flows accelerating to supersonic speeds. This is Mach 0.8, so it's subsonic, but in between the particles, the flow accelerates to supersonic speeds. You get these shocklets that form. And so compressibility effects are going to be more important at higher volume fraction for a given Mach number. And so what we're looking at now is quantifying drag. And so we see good agreement against incompressible drag correlations when we're at low Mach. But as we increase the Mach number, the drag increases. We're now looking at proposing improved correlations. And what we're arguing is that the Mach number used in these existing drag correlations should be based on an effective Mach number that's based on the volume fraction, because we see for a given Mach number, as you increase the volume fraction, compressibility effects start to dominate. And we're also quantifying the pseudo turbulence as well. And so, my argument here is basically there's these high-speed gas particle flows are really interesting and have a lot of challenges well beyond what's the challenges that exist for incompressible flow. And now that particle resolved simulations at finite Mach number are just starting to come online over the last couple of years, I'm anticipating an explosion of new models to come online. But all of this should be grounded in theory or strong mathematical framework in order to improve the predictive models for these flow regimes. So with that, I'm sorry I had a lot of slides in 20 minutes, and I think that's my time, but I'm happy to take any questions.
Thank you, Jesse, for the great talk. So we have a few minutes for 1 or 2 questions. I guess Professor Balachandar will have many questions here because a lot of citation to your work.
Yeah. Well, Jesse, one thing I noticed was in your simulations, towards the end, you had an interesting slide, and you didn't talk about it, but that's slide number 29.
Yeah.
After that crest, you see those radial streaks coming out. They were very similar to the movies that you showed. So in the movie that you showed at the beginning, so it was very interesting that your simulation is able to capture that kind of a phenomenon that was striking in the field observation.
Yeah, unfortunately, my student who did this work defended and is working at JPL, and we're sitting on this data set, and he's completely overwhelmed with his work at JPL. And so we haven't had any time really. I have a new student that's just starting to take this over, but there's a lot we want to do with this, and that we've just barely started looking at these simulations.
Jesse, I have a question.
Yeah.
Great talk, by the way. Really, really nice slides. I like the storyline a lot. So in incompressible flows, we are able to do homogeneous setups, right?
Yeah.
Whereas when you have this shock coming in from one side, doesn't it become intrinsically inhomogeneous?
That's a great point. Most of the PRDNS at these finite Mach numbers are of a case where you have like here you have a shock wave going through a bed of particles, which is sheds light on a lot of the physics and highlights the unsteadiness. The challenge is now your flow is unsteady and inhomogeneous. And so what we've been doing is this is a very similar case to the classic. This is a homogeneous box of particles with the mean pressure gradient, just like we have in incompressible flow. We've done a lot of work to be able to push the Mach numbers up, up to sonic conditions. And so there's no shock waves here. So these drag laws are not capturing the unsteady effects that you'd have from a shock wave. It's simply isolating the quasi-steady drag. You're at a given volume fraction. What's the steady state drag at a certain Mach number, so that we can get homogeneous and statistically stationary data.
Got it. Okay. Yeah, that makes more sense. Yes. Thanks.
It's not easy. It's a when you have the full compressible flow equations to deal with, it's a bit more challenging than incompressible flow to get these. But I've had a postdoc working on this for over a year, and now we're just starting to get data and analyze it.
Great.
So
I think
I've had here.
Hi, Jesse. Really nice work. I enjoyed your talk. Did you get a chance to look at the effects of gravity? Do you know if that plays any role? Because I would imagine near the ground, near the bed of particles, gravitational effects would be significant.
Oh yeah. So what's interesting, depends what you're looking at, right? So on Mars, gravity is about 1/3 of that on Earth, and on the Moon, it's even smaller. Gravitation, the Froude number is just enormous, right? So what we're looking at now is the effective pressure ratio on the crater dynamics and ejecta. I don't think gravity is playing a large role, at least at the early stage. So I think gravity is probably going to play a bigger role at later times, potentially, as things settle. But these are very expensive calculations. So this one at the end is an Euler-Lagrange with like 30 million particles. So we're only looking at the early time transients. And the Froude number is like order 1e⁹, right? So so I don't expect gravity playing a big role here, at least under these timescales we're looking at.
Got it.
And I'd just like to say, I'm hoping, fingers crossed that in the next couple of weeks, things don't get crazy and I can see a lot of you at APS. I know Hussein will be at APS and Shankar, and I hope to see you, Bala. So yeah, I'm really looking forward to seeing people in 3D again. And thanks again to the organizers of this meeting. It's been fun and great seeing a lot of friends here.